The biggest question was this: can AI become better than the humans that trained it? Imitation learning tried to solve AI by copying expert behavior. Watch humans, learn patterns, repeat actions. But there was a problem. If models only imitate humans, they can never go beyond them. That is where RLHF changed everything. Humans compare outputs and rank which response they prefer. That preference data trains reward models. Then reinforcement learning methods like PPO optimize the policy using those rewards. And sometimes, the resulting policy becomes better than the original demonstrations. DPO approaches the same problem differently. RLHF explicitly learns a reward function. DPO skips that step and directly optimizes the policy. But both methods still rely on the same important idea. Do not move too far away from the training distribution, because once models generalize beyond the data, performance can collapse. Researchers explored this idea in education systems. Thousands of students played a fractions game where laser beams fueled spaceships. The challenge was deciding which activity should come next. Different levels, different visuals, different difficulty. Using reinforcement learning, researchers learned policies that increased student persistence by around 30%, not by copying experts, but by learning better decisions from historical data. That leads into offline reinforcement learning. Instead of collecting new data live, the system learns entirely from past trajectories, medical records, educational systems, robot interactions, human decisions. But offline RL has a huge challenge. How do you evaluate actions that were never actually tried? This led researchers toward importance sampling, a method that reweights old data to estimate performance under a different policy. No simulator required, no explicit dynamics model required, but there was still another problem: coverage. If your historical data never contains certain actions, you cannot reliably evaluate policies using those actions. So modern offline RL became conservative. If the model has not seen enough data for a state-action pair, assume uncertainty. Be pessimistic. Stay close to regions supported by real evidence. And that same principle keeps appearing everywhere. RLHF, DPO, PPO, offline RL. Generalize carefully. Improve policies carefully. Because optimization without constraints can become dangerous.